All right, this is AP BC Calculus. We're doing a BC only section. This is Unit 10, Section 4, the integral test for convergence. So the first thing I want to note is that this is pretty far down the checklist. Despite being 10.4, which is pretty early in the Unit 10 section, for me personally, this is one of the last tests that I use if I've exhausted all of the easier ones or most of the easier ones. So I'm not saying that you shouldn't know the integral test. It is definitely tested on AP BC. By the College Board, but what I am saying is that although this is ranked pretty quickly and early in Unit 10 according to the College Board, it's definitely something that's farther down my own personal checklist when I'm looking for convergence and divergence. So the integral test says let a sub n, meaning that nth term inside a series, be equal to f of n, such that if you replace the n's with x's, you'd have a function f of x, and f of x is continuous, positive, and decreasing on some interval from b to infinity, right? So then the infinite series, right, summing from, let's say, n is 0 to infinity of that a sub n, behaves the same as the improper integral. Now, that's not to say that they have the same value, okay? So I want to highlight this behaves the same. It's not the same value, right? They're not the same number. They just behave the same. So if the integral converges, then so does the series. If the integral diverges, so does the series. But they don't converge to the same number. So if the integral converges to 5, it doesn't tell you that the series converges to 5, it just tells you it converges, okay? So if the integral converges, so does the series, but we don't know what the series converges to. So we don't know what the series converges to. It's not the same value. So far, the only kind of function that you know where you can say what a series actually converges to is when we're talking about a geometric series. You can talk about what a geometric series converges to. That's the only one. So this is never my first choice when I'm doing stuff. How do you spot an integral test? Typically, your a sub n is going to look something, it's going to look like something that you would integrate with u sub. Very, 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 very often, it's going to involve a natural log of n. In fact, when we're about to do 4 problems, 2 examples and 2 practice problems, and I think 3 of the 4 involve a natural log. It's that common. All right, so let's go ahead and walk through this. So we're going to apply the integral test. All right, so let's walk through it. Example 1. So we are applying the integral test. We're told to apply the integral test, so we can sort of like in our heads cheat a little and know that the integral test must apply because we weren't given the option of saying it doesn't apply. But let's go ahead and make sure it applies. So the first thing we have to check, right? So this thing is my f of n, right? F of n. So f of x, which would be 1 over x natural log of x, right? So that has to, 3 things have to be true for f of x in order to apply the integral test. Number 1, f of x has to be continuous. Well, the only 2 things that would make this thing discontinuous are when x is 0, which it can't be, or when x is 1, because the natural log of 1 is 0. But notice that since we start at 2, right, since we know that we're starting at values of 2, we're continuous on that interval, right? Second thing, we need to show that f of x is positive, right? Well, 1 over x natural log of x, right? X is definitely positive for x values greater than 2. That's fine, right? 1 is definitely positive. And then the natural log of x, if you look at a natural log graph is 0 at 1. So starting at 2, it's definitely always a positive. So that's all good. This is also positive, so check, we're positive. And the third thing we have to check is that f of x is decreasing. And there is a longer, more difficult way to do this, but you can kind of intuit this logically because the top is a constant, right? It's staying the same. And the bottom is getting bigger, right? Because this is increasing and this is also increasing. So if the denominator of a fraction is increasing and the top is constant, then the value of f of x has to be decreasing. As the denominator gets physically larger than the actual fraction, like the whole fraction must be smaller. So we can definitely apply the integral test, right? So now that we know we can apply the integral test, we want to look at this integral. And one of the reasons that I strongly dislike the integral test on a free response is because you're not really allowed to integrate improper integrals with infinity as a bound. So you have to do that annoying thing where you call this the limit as b approaches infinity and you integrate from 2 to b. Now, if I'm doing this on multiple choice, I'm going to be 100% honest and say that I just legit don't care enough about this to do that. And in my head, I just keep infinity as a bound. But technically, if you're doing this on a free response, you have to rewrite it as an improper integral. So I'm going to do the work without the bounds first, though, because I know that this is probably u sub, and it's easier to just integrate with no bounds for u sub and then go back and deal with the bounds. So my u is the natural log of x, and then my du is conveniently everything else that happens in the integral, right? There's my 1 over x and there's my dx. So this is essentially the integral of 1 over u du, meaning that this thing becomes the natural log of the absolute value of u. Great. So when I go ahead and put together my work without bounds into this thing that now has bounds, right? Let's do one more thing without bounds. This would be the natural log of the absolute value of the natural log of x, right? Okay, so the natural log of the natural log, cool. So now when I put my work together with bounds again, right, because this was my cheating where I'm just pretending there aren't any bounds, now that I put my work back together with bounds, and we'll actually go over here and do it so I have a little more space, right, I get that this is the limit as b approaches infinity of the natural log of x with an absolute value from 2 to b, right? So that's going to be the limit as b approaches infinity of the natural log of the absolute value of the natural log of b, right, minus the natural log of 2, right? Well, this is a small finite number, and the trick here is that this is going to be infinitely large, because if you picture what a natural log looks like, right, so here's a natural log graph, right, as x goes to infinity, a natural log graph goes to infinity also. This is going up forever, right? So I get something that's infinite minus something that's finite, meaning I get something infinitely large. So this thing diverges. The integral test says that these two behave the same. So if the integral diverges, then this thing must also diverge. And that's it. Now, again, the frustrating part about the integral test on a free response is there's a lot of tedious stuff that we can kind of skip mentally, but that mathematically we need that proper notation, right? So I can't actually integrate from 2 to infinity. I have to do it as the limit as b approaches infinity, which is kind of tedious, but it is what it is. Let's go ahead and do a P1. Same exact situation, right? Yet again, we're probably going to see that my u is that natural log of n. That's going to happen a bunch of times. So let's double check that we can apply the integral test, right? Does the integral test apply? So we know that the f of x we're using is just that entire function on the inside, right? But with x's instead of n's, right? So first thing, is it continuous, right? Well, it is, because again, the issues would be that x can't be 0, right? And we saw that x can't be 1, but since we're starting at 2, right? Since we're starting at x is greater than 2, we're good, right? Second thing, is this thing positive, right? Is f of x positive? That's the next question, right? Well, same argument again, right? So 1 is a positive number, right? X is positive for x greater than 2, so that's good. And the natural log of x quantity squared is definitely a positive for x values that are greater than 1, so we're fine, right? So definitely positive. And then the last thing, is it decreasing? And the answer is yes, it's decreasing for the same reason we saw before. This is a constant, right? And this bottom is getting bigger, right? So this, the bottom is increasing, which means the entire fraction must be decreasing. So again, it's good to do a quick mental check that you can apply the integral test. It's very rare you're going to be specifically told in a problem to apply something and then not be given an out, like, or say that the integral test doesn't apply. And they didn't give you that out here, so it's very likely it's going to apply, but still technically we should check. So now let's go ahead and do the integral test. We're going to integrate from 2 to infinity of a 1 over x natural log of x quantity squared dx, right? Which we know we actually have to do as an improper integral with the limit, and I get that that's tedious. Again, on multiple choice, I'm going to own it. I totally cheat and just consider infinity to be a bound, which you really shouldn't do, but I totally cheat. So I'm going to do work without bounds, right? Work without bounds, and I make it really clear that this is separate work, right? I'm showing what happens if I integrate without bounds, and this is yet again classic u sub, right? My u is going to be the natural log of x. My du is conveniently everything else outside of that. So you'll find that this is usually pretty easy u sub, right? So it's going to look like this, or I'm integrating a u to the negative second du. So when I do that, I get a negative 1 over u, or this is a negative 1 over u was a natural log of x. So that's my work without bounds, and then I can kind of cheat. I will say that sometimes, depending on the person, depending on who you are, sometimes that work without bounds is something that happens just in your head, that you legitimately can jump from there to here, and that's not cheating, right? Depends on the problem, but most of the time it's not a big deal to be able to do that. It's definitely not cheating. Remember, your job is to communicate understanding. Oh, sorry, this was a B up here, my bad. Fixing it, it's B, because that's why we did the limit. Anyway, so now when I plug in, I get that this is the limit as B approaches infinity of a -1 over natural log of B minus a -1 over the natural log of 2. Well, this is a finite value because remember that this thing is going to be infinitely large, right? As I plug in an infinity, that thing's infinity. So this thing becomes a 0 plus a 1 over the natural log of 2. So that integral, the integral from 2 to B, right, this limit as B approaches infinity, actually, I can write what the integral was. I just had to clean it up to evaluate it. So the integral from 2 to B, that improper integral of this ugly mess, right, this thing here, it just equals a 1 over the natural log of 2. Now that's the value of the integral. What that means, right, and this is an important distinction, it means that this thing converges. It doesn't converge necessarily to that value, okay? So what this tells us, right, so this converges, so the integral converges to this value. That means that the series, right, so just to be clear, the series converges, but we don't know to what value. So it converges because it behaves the same, right? Either converges or diverges, but we don't know to what value because it's not the same as the integral, right? It's not the exact same value. So the integral converges to 1 over natural log of 2. The series just converges. We don't know more than that, and just want to be clear about that distinction. Okay, let's go ahead and do 2 more. All right, so this one looks awful. I'm going to make the argument that it's actually no worse than the other ones we've done. So I'm going to go ahead and say that my f of x is a 1 over x natural log of x, and then a natural log of the natural log of x, which looks awful, right? I need to show that f of x is continuous, right? Well, f of x is continuous. Notice they start at 3 because the discontinuities would happen when x is 0, when x is 1, right? And when this inside thing is 1, which would mean when x is e. So so these are the 3 discontinuities. Discontinuities, I ran out of space. So x being greater than 3 is fine, right? Because e is slightly smaller than 3, it's like 2.8, blah, 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 right? So x being greater than 3 is fine, right? I have to show that f of x is positive. Well, same argument, as long as I'm bigger than these values, right? So x, natural log of x, and the natural log of the natural log of x are all positive for x values greater than 3. So we're fine, right? And then 1 is obviously positive. And I need to show that f of x is decreasing. We've used the same argument every time. The top is a constant. And then the other 3, x, natural log of x, and the natural log of the natural log of x, are all increasing. So the whole fraction is decreasing. Right? The whole thing has to be decreasing because if the denominator is getting larger, then the entire fraction is decreasing, right? Again, now if the numerator were also changing, we'd have to pay more attention, but the numerator is just 1. So we can definitely apply the integral test. So now we have to do that same thing where we set up this ridiculous integral that we really just wish we could leave as an improper integral, but unfortunately we have to use the stupid limit as b approaches infinity, blah, blah, blah. So I get this, right? And I recognize that unfortunately, if this is free response, I need to be very clear that I'm using a limit because you're not actually allowed to use infinity as a bound, even though it's super tempting. All right, so, and then I have to pick my u. So let's go ahead and do my work without bounds. Work without bounds, right? When I do my work without bounds, I'm going to guess that this is my u. And the reason I say that is because magically everything else in the integral is du if this is my u. So my du would be 1 over the stuff times the derivative of the stuff. Oh, look, that's everything else. That's this thing times this thing. So I end up getting that this is the integral of 1 over u du, right? Which means I'm getting that this is the natural log of the absolute value of u. And this is where it gets a little crazy, because this means I'm getting the natural log of the natural log of the natural log of x. All right, so what that means after I do my work without bounds, natural log of natural log of natural log of x, is, I think I was using blue for the top. and it's 3 to b. Okay, so if I go ahead and plug back in, it means that this integral, the integral from, so limit as b approaches infinity from 3 to b of 1 over x natural log of x times the natural log of the natural log of x, is going to be the limit as b approaches infinity of natural log of the absolute value of the natural log of the natural log of x, evaluated from 3 to b. So I'm going to get that this is the limit as b approaches infinity of the natural log of the absolute value of the natural log of the natural log of b, yikes, minus the natural log of the natural log of the natural log of 3. Well, this is just a finite number, and this gets infinitely large, right? Because we've seen, it doesn't matter that I've got layers of natural logs, these things all go up forever. So this thing diverges. Once I know this diverges, I know the series also diverges. Now, I'm going to be honest and say that I probably would stop right about here. I would stop right about here because I'd recognize that I know natural log gets big forever. So if the natural log is on the top of a fraction, then this thing's going to be divergent. So notice if we go back one slide, the difference here, right about here, I know the answer. Because I see that the natural log's on the bottom, I'm like, yo, that's great. That's going to be a 1 over an infinity. That's a finite number. So if you look at these, as you get good at them, like when I got to here and said, oh, look, it's a regular natural log. As I go to infinity, that's infinitely large. I can pretty much stop and be done. So it does get a little bit easier as you get better at doing these. All right, so let's do one last one. So this is an e to the 1 over n all over n squared. Okay, so I have to go through the list. So we know my f of x is an e to the 1 over x over an x squared, right? So the first thing I have to show is that this thing is continuous. Well, as long as x is not 0, I'm good. So it starts at x is greater than 1, so we're fine. Second thing, I have to show that this thing is positive. Well, e to the 1 over x is always positive. And x squared is positive for x values that are not 0. And since we're starting at x is greater than 1, we're good. Okay, cool. And the third thing I have to show is that this thing is decreasing. Right? Now this one's a little bit trickier to show that it's decreasing, but sort of the logical way to think about it is that this numerator, right, so as x approaches infinity, e to the 1 over x is going to approach e to the 0, which is 1, but the denominator, x squared, is going to get huge. So the numerator is getting smaller and smaller and smaller, right? So this thing gets smaller, right? But this thing gets way bigger. Like this thing gets slowly smaller. This thing gets way bigger. And so what you'll see is that pretty quickly it's obvious that this thing is decreasing. Because remember, if the denominator gets bigger, if the denominator is getting huge, then the numerator is not getting changing, getting huge also. Then we have something that's decreasing. Now there is another way to figure it out. By essentially taking the derivative of this, but I think it's a little bit easier to just logic your way through the fact that it's decreasing. So we want the integral from 1 to infinity of e to the 1 over x squared dx, but we know we have to write it as an improper integral, so it's the limit as b approaches infinity from 1 to b of e to the 1 over x squared dx, right? So I'm going to go ahead and guess that this is my u, so I'm going to do some work without bounds, because that's the easiest way to cheat and not be miserable with your u sub. So I'm going to assume that my u is 1 over x, which means my du, right, that's an x to the negative, that's an x to the negative first. So my du is going to be negative x to the negative second dx, or a negative 1 over x squared dx, right? So that's basically this, but with a negative. So I'm pretty sure I get that this is the integral of a negative e to the u du, right? Which is going to be a negative e to the u, right? So once I know that, once I've done my work without bounds, I'm going to go ahead and plug back in. So we get that this integral limit as b approaches infinity from 1 to b of e to the 1 over x divided by x squared dx should equal, right, a negative e to the 1 over x, right, from 1 to b with that limit in front. So I'm going to get that that's the limit as b approaches infinity of negative e to the 1 over b minus a negative e to the first, right? Well, if you look at what happens when you plug in infinity, right, this ends up being a negative e to the 0, right? As you plug in infinity for b, you get a 0 up here, plus an e to the first. So I end up getting a negative 1 plus e. Now, that is the value of the integral, right? So so the integral converges to negative 1 plus e. What that means for the series, right? So that's what the integral does. So the series converges, but we don't know to what, right? It converges to an unknown value. Okay, so again, notice the difference. They behave the same, but they don't converge to the same value. And that is it for the integral test. Again, it's not at the top of my checklist of things that you should do when you're going through convergence and divergence, but if you see something with a natural log of n, it's a very likely possibility that it's the integral test.